Okay, we should be recording. All right. So today we're going to go ahead and finish up the equations of lines section. We're going to only talk about a couple things during this little video, and then you've got a second short, like 3-minute video to watch after this about how to do something on your graphing calculators. It'll be linear regressions. I, again, don't have a good enough setup to show you guys what buttons I'm pressing and all that stuff, and the other video is probably a little bit more clear and concise than I would make it anyway. So let's go ahead and get into this. So this is still chapter 2.1. This is part 2. You'll notice the assignment for this one is significantly shorter than the first one. The idea was to kind of give you, the more dense part earlier, so you had more time to work on it, hopefully more time to come up with questions to ask, and then this part should be hopefully a little bit less in depth, at least in terms of the amount of work you're doing. So we're going to talk about a couple of different things. We're going to start with interpolation, which is a concept that really applies to predicting and making estimates about real world data, but you can also use it just in functions that don't necessarily have to represent anything. But interpolation is the process of using a function to predict values at a point in between given data points. And so it's gonna help for all of this definition stuff to look at an example. But this process is primarily used when looking at real life models of data. And to understand this process, we want to look at some actual real life data ourselves. So interpolation, I need to figure out a good place to put this. Let's try down there. Anyway, so interpolation. This is the data we're going to look at to start. In 2004, there were about 4.6 million US digital music album downloads. In 2014, that number reached 117.6 million. We can write a linear equation to model this data as follows. And if you're following along in your textbook, this is the same example that they use. So first things first, we want to calculate our M. What we did here is we wrote these out as points. So we said that these are the X values in blue and then the Y values are in red. So we've got 2004, comma 4.6, and we've got 2014, comma 117.6. So these were the 2 points we used to calculate a slope of a line between the two, and we get 11.3 when we calculate that slope. So in point slope form, sorry, I know that's kind of hard to read, our equation looks like this. And the reason for using point slope form here is because all of these points are really, really far away from the origin, right? Your 2004 to 2014 for your X values. So switching it back to the origin would just mean that you're using really big numbers in your calculation. So in this case, it's going to be a little bit easier. So this is our point slope form equation. Y equals 11.3 x minus 2004 plus 4.6. And I just used the smallest point on this rather than you could have done 2014 and 117.6, but it wouldn't really, this will end up being easier. So we can estimate or interpolate the number of digital downloads in 2006 by plugging in 2006 for x. Now notice that 2006 here is in between 2004, which is our smallest data point, and 2014, which is our biggest. So if we plug in 2006 for x, we get y equals 11.3 times 2006 minus 2004, which is 2. This is why this point slope form is easier. So 11.3 times 2 plus 4.6, which is 27.2. So we can estimate that in 2006, we had 27.2 million digital music album downloads. Now let's look at extrapolation versus interpolation. So you've probably heard of the word extrapolation, extrapolating data. And that's just kind of making predictions on data that is actually outside of the range you've been given. So for starters, for interpolation, notice that because 2006 was within our data range, so between 2004 and 2014, we were using interpolation. If we were to use our formula to predict the number of digital album downloads in 2003, we would be using extrapolation, right? So that would be, if our function is, where'd my pen go? So if our function is like, let's say this is 2004 and this is 2014, right? If this is our linear, wow, okay, lines are hard to draw. Try that again. 2004, 2014, draw a line between those, close enough. The point 2003 would be like here. And so we're just kind of extrapolating that out, right? We're assuming that that trend continues. And then we could also do one that's in the future. which is generally actually more helpful, but it's not really the point right now. We're just looking at extrapolation, and this example will show why extrapolation can be kind of dangerous. So if we plug in 2003 for x, we get this. Y equals 11.3 times 2003 minus 2004, which is -1, plus 4.6. If we solve that out, we get -11.3 plus 4.6, which is -6.7. This tells us that in 2003, there were -6.7 million digital album downloads, which obviously that's not possible. We can't, I mean, I guess you could have uploaded 6.7 million, but I don't think that really qualifies here. So this shows us the danger of extrapolating. Similarly, if we looked at like the year 3000, you'd have, some ridiculous number of digital music downloads that just doesn't make any sense. And that's even assuming that computers are still used in the year 3000, which is probably stupid. So extrapolation can be kind of dangerous, especially the further away you get from your data set. So practice, let's look at an example here. In 2008, Apple sold 55 million iPods. In 2011, they sold 43 million. And we're going to be asked to do the following. So this is a lot of different points. We're going to take them one by one. But first, we want to find the point slope form of a linear function modeling this data. Then we want to estimate the number of sales in 2010, and we can compare that to the actual number, which was 50 million. And then we want to estimate the number of sales in the year 2023. And then at the very end, we're going to ask which year we're using interpolation and which year we're using extrapolation. You can do that right now if you really want to. It's pretty easy, but we'll get to that on its own in a little bit. So let's do a first, which is find the point slope form of a linear function modeling this data. So first we want to calculate our slope, and we're going to do the same thing we did last time. So this will be our x, so our y, y, x, and this will be 1, y1, and then x2, y2. So we get this, 43 minus 55 over 2011 minus 2008, and that is equal to, we solve that out, we get -4. It'd be -12 over 3, which simplifies to -4. So then we can use our smallest point. We're going to use the smallest point in terms of x. That just makes things a little bit easier. So using the point 2008.55, we can write our point slope formula. And that's y equals -4x minus 2008 plus 55. Remember, the general formula for point slope form is y equals mx minus x1 plus y1. And since our y1 is 55 and our x1 is 2008, we plug those in for x1 and y1, we get this. So this is our answer to A. Okay, now let's move on to B. So we want to estimate the number of sales in 2010, and we can compare that to the actual number of 50. So we've got our formula, y equals -4x minus 2008 plus 55. We'll plug in 2010 for x. That gives us -4 times 2010 minus 2008, which is 2. -8 plus 55 is 47. Okay, so this is equal to 2. -4 times 2 equals -8. -8 plus 55 is 47. So we got that there were 47 million albums downloaded, or number of iPod sales, sorry. That was the previous problem. Number of iPod sales in 2010. The actual number was 50 million, so we're relatively close. We're a little bit off, but it's not a huge margin of error there. That's not too bad. This means that our estimated value of sales in 2010 will be 47 million versus the actual 50. So yeah, I mean, you could do a statistical analysis to see how close that is, but that's not really the point of what we're trying to do right now. So the next one, we want to estimate the number of sales in 2023. So remember, using that same formula, we're going to plug in 2023 for our x. And that's going to give us this, which is -4 times 2023 minus 2008 plus 55. This gives us a -5. So if we do this out, we get, what, 15 here? 23 minus 8. So we'd have 15. -4 times 15 equals -60. And -60 plus 55 is -5. So this means that our estimated sales in 2023 would be -5 million, which again, probably isn't possible. So in this case, it's very obvious which one's interpolation, which one's extrapolation, because our extrapolation gave us an impossible answer. But the easier way to look at it is In B, we estimated the year 2010, which is in between the years 2008 and 2011. So that's interpolation, right? The data, the set or the number that we used is in between 2008 and 2011. In C, we estimated for 2023, which is not between these, so we used extrapolation. And I guess if you really want to, you can think of it as like excluded from this data set, or extra, it's going further outside. However you want to remember those, but hopefully they're not too terrible. If you're predicting the future or predicting the past further out than you actually have measured data, it's extrapolation. If it's in between your points, it's interpolation. So the last thing we want to look at in this video is modeling semi-linear data. So in some cases, you're going to get data that looks, whoop, there's the table, like this. So you'll notice that each one of these is moving 2 years, right? So our, I guess, run would be 2 if we're calculating a slope. And here we got a difference of 6, a difference of 6, and then a difference of 7. So this is almost perfectly linear, but this last point is just a little bit off. So in cases like these where the data is really close to linear, we can model it using just our 2 endpoints. So in this case, we could use this number and this number and this number and this number, and we could model that with a linear slope. And it's not going to be terribly inaccurate. So if we do this, we'd get what? 88 minus 69 over 2019 minus 2013, which is equal to 19 over 6, which is about 3. It's 3 1/6 would be our slope. And so since each of these is 2 years, you would expect it to go up by about 6 1/3. So we go 6, 6, and 7. So it models it pretty accurately. In cases like these where all of your points are really far from the origin, point slope form is usually more helpful than slope intercept form. And that's for the same reason that we looked at earlier. When you're subtracting those big numbers, it's really helpful to have it just as a point form, so you're getting rid of those extra variables. So in other cases, you might get data that looks highly unorganized. Anytime we use a linear function to approximate data that uses one variable to predict another, so anytime we have a y equals something x, we are using what is known as a linear regression. So if it's modeling real life data that like has a bunch of points, right, and we use a line to try to approximate that data, we're doing what's called a linear regression. Doing an actual like linear regression, calculating it out is actually really complicated, which is why we use the graphing calculators to do these. But the statistical method used to determine linear regression is based on the method of least squares. So it takes the absolute shortest distance between every single point and the line and finds what line fits them the best. And it's very complicated. That's like advanced, I think it's probably calculus to be able to do it correctly. So we don't actually learn how to do that. You're just going to use your graphing calculators, and the video you watch after this one will show you how to do that. But there's some important things you need to know about it before you go into those. First, we want to look at correlation coefficients. So when you use a calculator to calculate a line of least squares, which is also kind of called a least squares line or a line of best fit, you'll see all 3 of those terms probably in your homework. I will probably use the line of least squares the most, just because it's the most technically accurate. The calculator will compute an R value. The R value is the correlation coefficient, and it will always be between -1, this negative should be down at the bottom. It will always be between -1 and 1. Positive. So as we can see here, this is a positive correlation, which means the line that fits these the best is going up. This has a negative correlation. They're going down as it goes, and then no correlation because this data is just not any other direction. So looking at R values really quick, and this stuff hopefully is review. You've probably seen this in science class, hopefully in a math class before, but an R value of -1 represents a perfect negative correlation. So this is close to perfect, but if every single point was exactly on our line, this would have an R value of -1. It's going down, so it's negative, and the closer to 1 it gets, the more accurate the actual correlation is. An R value of 1 represents a perfect positive correlation, so this one's pretty close. Again, if every single point was directly on this line, it would be a slope of, or an R value of 1. And then an R value of 0, which would be like with this one, represents no correlation. So that means that there's no line you could draw through this that actually like resembles this data in any way. You can't really, I mean, like a line like this looks just as accurate as a line like this at this point. So you can't really draw a line through this data that actually represents it. So you'd get an R value of 0. The closer an R value is to 1 or -1, the stronger the correlation. So for instance, this would have an R value of very close to -1. This would have an R value of somewhere closer to like maybe negative 0.6. So it's not nothing. There's a correlation there, but it's pretty weak. You can see a lot of these data points don't really fit anywhere close to this line. This one would be very, very close to -1. This is a really strong negative correlation. This would be really close to +1 because it's pretty close. This would be kind of in between, maybe like a 0.5. You've got a lot of points that are a little bit off. And then this is, of course, going to be that 0. So the closer an R value is to 0, the weaker the correlation. Okay, so to calculate a line of least squares fit, or a line of best fit, or least squares line of a set of data points, you're going to want to use your graphing calculator. The second video is going to show you how to do this, as well as how to view the line and the data points on your calculator in a graph. And calculating a line of best fit by hand is incredibly difficult. It takes a lot of time. So I'm just warning you extra here. Don't try to do it like that. I'll link this video in the actual Google Classroom. But that's all we've got for this lesson today. Please watch that second video before class. If you have any questions, please come to class prepared to ask them. Hopefully we can get those clarified for you guys and get you plenty of time to work on your homework and stuff. But I will see you all later.